look at an interesting bit of demography, but also we refer to it as the science because it is one of the key analysis that individuals do in order to understand how their population might live for the next periods. But also many statisticians use it to project utilization of different health facility services. But also not only statisticians use it in the scientific field, what we call survival analysis is used in business settings as well to determine how consumption of some of the products business individuals produce might last. So in this particular lecture or in this module itself, we want to look at that by the end of this particular module or lecture or lectures, the students should be able to understand some of the following issues. That they should be able to understand the key terms and definitions in survival analysis. They should be able to identify or understand the sources of survival data, but also the measures of survival. And there are very many different measures which may not be included in the objectives here. We shall get the deeper understanding as we proceed. But mainly we have plan measure of survival, but also the Cox measure of survival and the parametric module. And these are models that help us further analyze what we call survival in here. So for the start, we want to start with the key terms that we have to use in survival data. But before that, we just want to, you can save data. So it can be death, can be birth, but also can be failure or recovery. In failure, we could mean that possibly there is an activity. So preceding this particular introduction to survival analysis, remember we looked at what we call probability. And survival analysis actually fits in part of the use of probability. There are some of the concepts that go hand in hand because in survival analysis, the aspects of probability also come in there because we want to understand the timeline or the possibility that an event will occur at a certain time. So it assesses whether a participant experiences the event of interest during the study period. So this assessment is typically represented using a dichotomous or indicator variable. So dichotomous meaning we're looking at uh, uh, two two outputs. We're looking at either yes or a zero, and the possibility of an event occurring rhyming beyond from 0 to 1. So dichotomous, you're looking at 1 and 0, or in statistical analysis, you could be looking at 1 and 2, but later you code them back to 0 and 1 because they are the ones that give you the occurrence where 1 codes the occurrence of an event and 0 codes the event's non-occurrence. So here we're looking at whether a death can occur or a death might not occur, or whether the patient might recover from taking a particular medication or the person may fail to recover. So that is what we were looking at in assessment. But you should be able to understand from there survival data. So another key concept here is survival. Primarily, a condition where an individual or group remains alive after a specified interval. And secondarily, a condition where an individual or group maintains membership in the group of interest. such as a school enrollment cohort, marriage, marriage cohort, or the non-poor population. So here we're looking at someone's survival within a particular group. Say we expect, for example, that in Uganda, the the expected life the life expectancy is 63 for men and 65 for women, and therefore anyone who lives beyond who lives still who lives in that particular age group is lives in survival. Similarly, when people enroll in a school, for example, let's say the class of 2018, and then we say they are for their pre-primary, and it is supposed to be for 3 years. So by the third year, the number of children who enrolled in the beginning of the pre-primary who survived throughout to the third year is what we call survival. Likewise, in a marriage cohort, in the cohort meaning a group of married individuals, the ones who survive that cohort and remain married to a certain level or to a certain time specified interval, that is what we call survival. And another term is what we call the survival curve. We shall look at it later on, but in simple terms, the survival curve is a graph depicting a survivorship function, meaning the number of people who survive in a certain period of time. And most times you might start from 1 down to 0. So it would mean that when individuals are born, the level of survival travels from up down that specific curve down to 0. For example, from 0 point this to 0 point this, and you will be able to see that people who can you still see my screen? Can you confirm if you can see my screen? Okay. If you can't see my screen, you can see the screen. Kindly confirm.
Yes, the screen is visible.
All right. Thank you. So
The
another
screen
term,
is not visible and the tone is too low.
the voice or my voice or okay, you confirm by putting by just putting your hand as a tick so that yes or pure.
Yes, sir.
Yes.
I think the screen is too tiny and the volume is a bit too low.
All right. Let me adjust. Can you confirm that? Kindly confirm, so that I.
It's visible to me
It's
according.
okay now.
All right. So we're looking at the aspect of survival curve, and I said it just looks at the survivorship function, how individuals survive over a period of time. So the probability of survival always keeps on. For example, if we're looking at that, people will get extinct by 63 years in Uganda, and therefore the possibility that they will survive may start from 1 and drops up to 0, or it might increase the possibility that someone will be able to die will increase from 0 to 0.1, 0.2, 0.3, 0.4, 0.5, and when people reach 63, according to the life expectancy, it is expected that the probability of death will be 1, and that is what we're looking at regarding survival curve. Another key term is what we call the survival rate, and it's a rate expressing the probability of survival of a population group, usually an age group, from one date to another and from one age to another. A survival rate can be based on life tables or two censuses. So when based on two censuses, the rate includes not only the effects of mortality, but also the effects of net migration and relative census enumeration errors. So to calculate the survival rate, we are looking at a rate that expresses the probability that someone may be able to, the chance, and this chance we're representing it in terms of a rate, meaning that it has got a denominator and a nominator, and then it is subjected to a rate as 1,000 or a rate as 100. And therefore, we shall be looking at the probability that an individual is surviving. And most times we're saying that these are organized in cohorts. For example, if it is using a life table, the cohort might be 1 to 4, meaning the survival rate will be calculated using the number of people that were born. For example, in the age cohort 1 to 4, the number of people that were born in that particular age group that survived to the next age group, meaning the ones from 1 to 4 who survived to the age group of 5 to, let's say, 9. So that is what we call the survival rate. We shall be able to calculate the number of people who survived and subjected to the rate of 100. And another key concept is what we call the survivorship function, and the probability that, yes, Godfrey, your hand is up. Godfrey, your hand is up. You have a question? If not, kindly mute. You can as well raise down your hand. Please mute. So the survival function is the probability that an individual survives to time t, before an event of interest, for example, death occurs. So it is one of the three algebraically related functions used in survival analysis. The other two being the death density function and the hazard function, which we shall look at in the next as we proceed. So the survival function is found by dividing the death density function by the hazard function, meaning we're looking at what is the possibility that someone will survive given the hazard function, meaning given the circumstances that are around. For example, taking into consideration the disease adjusted life years. So, in other words, we shall be looking at what is the possibility that someone survives to time X before death. So, before someone dies, what time will the person take in what we call the survivorship function as a key concept. We shall continuously look at this as we continue. And then another key concept is death. And when we're talking about death, we are referring to the permanent disappearance of all evidence of life at any time after a live birth has taken place. So the loss of a member of the population as recorded by the death certificate. So we're looking at that there is no evidence that this person is alive at all. And most law or legal documents would want to see what we call a death certificate that confirms that there is definitely no evidence that this person is alive. But this is only subject to the event that there was a live birth that occurred. For example, so we do not look at still or macerated death when we are referring to death, because virtually there was no live birth. Of course, this definition has been criticized by different people, including the religious sects, because, for example, the Catholic Church believes that life begins in the womb and with the formation or with fertilization. And therefore, they may not agree with the fact that we're looking at any time after a live birth. However, for us, our take home is that we're looking at the event that there was a live birth. Secondly, we're looking at death density function, the probability that a death, or more generally, an event occurs during a given time interval. No matter how small the interval, it is a probability density function where the random variable is time. So it is one of the three, like we said, related functions broadly dealing with the issue of survival. And again, we are saying here the others are the hazard function and the survivorship function. So the death density function, we also look at the aspect of time, and it does not matter whether it is a small interval or it is a large interval. And we want to conclude possibly the key concepts for the issues of survivorship here by looking at hazard function. And we're saying that it is one of the three algebraically related functions used in survival analysis. And the hazard function is found by dividing the death density function by the survivorship function. So then we can be able to understand the level of hazard that an individual can be subjected to. And then the other key concepts in survival analysis include the follow-up time, meaning the follow-up time is a critical component of survival analysis because it measures the time interval from the time origin. When a participant are considered at risk to the event occurrence, study end, or participant loss, whichever occurs first. So for example, in our life table, we expect that if an individual clocks the age 65, for example, in Uganda, the life table indicates that if an individual clocks the age 65 for female and 63 for male, the average life that an individual is left with is about 25 years to 30 years. Likewise, if an individual reaches the ages of 80 or of 75 to 80, the average years they can live are 15 years. So in this time, we would be able to understand a follow-up time, meaning the event that a person is at risk of dying in 15 times, in 15 years when they clock 75, vis-a-vis the time when that event occurs, the event being death in that regard. Then we also look at the term of time origin. And we're saying it looks at time zero, or the time origin is the starting point when participants are considered at risk for the outcome of interest. So in this time, we can say we can look at time zero being the age of 1 month or of 1 day when an individual is born to the time of death, and that is then we shall take time of birth as the time origin. So it varies depending on the type of study, such as at enrollment in cohort studies or randomization in clinical trials. So for clinical trials, for example, if we wanted to look at the COVID vaccine, we would look at the time zero possibly being when an individual receives the trial vaccine, say on this date, then that would be the time of origin throughout the time of study when an individual is offloaded off the cohort study on maybe the clinical trial regarding COVID-19. Then we look at the minimum age criteria. And in prospective cohort studies, a minimum age might be specified as an inclusion criterion. For example, participants may need to be 55 years or older for a study on stroke risk, or 35 years or older for a study on cardiovascular disease risk. So if you wanted to do survival analysis, you may not do survival analysis on some age categories. You will have to have a criteria through which you can be able to subject a particular population to a particular study. And so we are saying whereas this might be possible in some situations, it may not apply. You may not be able to subject a 20-year-old person to a diabetic disease risk assessment, because we understand that this is an age where the risk may not be as much as a person who could be above 35. So these are some of the risks that you have to assess. You cannot maybe subject a woman who is in her childbearing age to complications of delivery, or you may not subject a woman who has attained a certain level of antenatal care visits to a certain risk compared to those that may not attend regular antenatal visits. Then 4, we're looking at the recording entry time. Participants enter cohort studies and clinical trials over months or years or even days. So it is crucial to record the entry time to measure follow-up time accurately. So you need to be very sure when we're talking about recording entry time, we want to determine when this individual was able to enter this particular study or the clinical trial. And number 5 is what we call censoring in survival analysis. So censoring in practical terms means that not all participants experience the event of interest within the study period. So for those who do not experience the event, follow-up times are censored, meaning that they are ignored or they are suspended and representing the last observed time point before the study ends or the participant is lost to follow up. So in censoring some of the individuals, it is a data gap that occurs, that some individuals may not be followed up. They become lost to follow up. For example, if you are doing a clinical trial on a particular medicine in a community, some community members might migrate, or some of the members might leave, or some of them may die and you may not trace them. So some of that gap is censorship of data in that regard. So we want to look at some of the sources of survival data. And we're saying that we look at clinical trials, we look at epidemiological studies, and reliability engineering. So in clinical trials, this is subjecting individuals to certain studies that want to give a clinical result. For example, we call them vaccine trials, we call them drug-resistant trials, but also we look at effectiveness of vaccine drugs and different antigens that individuals try to administer to individuals so that they understand the rates or the effectiveness of that particular drug. And that is what we call a clinical trial. Then we look at the epidemiological studies. Most times that we try to look at the cause and effect of certain diseases, or they try to understand the spraying pattern, or the pattern in which these diseases may be sprayed spread across a population. And those are the different scientific studies that epidemiological surveys consist of. Then, when you're talking about reliability engineering, you're trying to understand how a population or a particular area of interest may adopt to a new innovation that has been done. So you want to understand how reliable, possibly maybe, for example, in GMOs, how reliable this might be in a particular area, in maybe that is facing a different type of climate. So censored data. Censoring, this happens when some subjects do not experience the event during the study or period, as we said earlier. And we said it means that the exact survival time for these subjects is unknown, and only a lower bound can be estimated. So therefore, you may not need to include them in your study. So what are some of the assumptions of non-informative censoring? That in survival analysis, we often assume that censoring is non-informative, meaning it does not affect the prognosis. Therefore, those individuals who do not face that particular event that you had subjected them to, you consider them to be non-informative, in that they do not affect the prognosis of what you're trying to understand. And this assumption is crucial for unbiased results, because then if you assume that they might be there and they might affect your study, then it becomes an issue that might be showing biased results. Therefore, you try so much to ignore lost to follow up individuals in that particular study of interest. Then we look at competing risks. This happens when multiple possible events can terminate the survival time, such as death from different causes, competing risks after the probability of observing the event of interest, and require specific methods to account for them. So here, when we're talking about competing risks, for example, if you wanted to understand the survival time of a diabetic patient, you might realize that because diabetes could come with underlying conditions such as high blood pressure, that becomes a competing risk. And therefore, an individual might be affected by a competing risk of high blood pressure, and then yet you were subjecting the same individual to the possibility of dying as a result of diabetes. So that might my screen is showing that it is not being shared. Let me just reshare it here. So that would mean that the person succumbs to a different risk vis-a-vis the risk that you were subjecting the person to. And we just want to tap into what we also refer to as heterogeneity. And this happens when there is a different subgroup of subjects that have different survival patterns, such as age groups, gender groups, or treatment groups. Heterogeneity means that the survival data is not homogeneous and may need to be stratified or modeled using covariates, meaning that this in heterogeneity we mean that these are not the same groups, and therefore, because they are not the same groups, they experience different survival groups. I mean, survival patterns across different age groups. So we may have gender groups. We may have females, which is a homogeneous aspect. But among females, we may have married, unmarried, urban, rural, poor, rich, or in that income strata, we may have those who are in a reproductive age and those who are not. So these are what we call heterogeneous, meaning that they have different patterns, and therefore all these people experience different survival patterns, and therefore you may have to remodel them in your study in order to have a homogeneous study group. So meaning that you may have to look at marriage as its own, and therefore instead of only looking at females, which is a homogeneous, you have to look at furthermore among the females you decide to look at marriage patterns, and therefore you would have to look at separated, you would have to look at never married, you want to look at those who are divorced or separated, but also you'll have to look at those who are married in terms of marriage or pattern or marriage status. Then, if you're looking at residence, you'll need to go and further look at whether people are living in the rural areas or they are living in urban areas, as a way of further trying to model using covariates and make sure you get a very a group that is homogeneous as possible, so that you can be able to understand their survival rates in that regard. So like we said in survival curve, in our definition, we want to understand further a survival curve in here with the illustrations. And we are saying that it is a graphical representation of the probability of survival of a group of individuals over time. And it can be used to compare the effects of different treatments, interventions, or environmental factors on the survival of a population. And this graph here just shows the survival curve of smokers. So we're saying the thousands of survivors. So you can be able to see from the upper peak, uh, people who are non-users would take more time. For example, we are looking at from the age 30 years. When you look at the dotted line where it is reflecting heavy smoker, moderate smoker, and non-user, you can be able to see the probability, the survival curve. You can be able to see that whereas when we reach 40, when we reach 40, whereas we see about in 40 years we see about 90 people for us in those who are heavy smokers. In 40 years they are about 80, and you can be able to see the graph moving, and you can be able to establish that whereas for those who are non-smokers, uh, at 70 years they would be surviving, there would be about 45 people surviving. Looking at this particular, I'm looking at this intersection here, there could be about 45 people surviving, 45,000, 45,000 people who are non-smokers who are surviving. But for us at age 70, for the heavy smokers, there are only about 35,000 that are surviving. So you can be able to see that survival curve for those who are smokers in that regard. So the survival curve information. Uh, just excuse me a little. I take a sip of water. I have some cough a little bit here. So the survival curve information, in the median interval time, which is when 50% of the individuals are still alive, is what we call the medium survival time. It is what we call the median survival time, meaning that 50% of the individuals are still alive. So in 50%, you're looking at this figure here, uh, 50,000 out of 100,000 people. You can be able to see that 50 is our survival point. And this is what we call the median survival uh, point. And you can be able to see here that we shall have non-users at about age 60 something, and we shall have the heavy smokers at about 60, and their numbers are relatively very small in that regard. So the hazard ratio, which is the ratio of instantaneous death rates of two groups at any given time. So a hazard ratio of 1 means the group have equal risks of dying, while a hazard ratio greater than 1 means that one group has a higher risk than the other. So you can be able to see here that that the heavy smokers have a higher risk of death than the non-users, and therefore the risk of dying is more among those who are heavy smokers. Then the mean survival time is the statistical measure of the average time an individual or group of individuals is expected to live after being diagnosed with a specific condition or exposed to a risk factor. It is often used in clinical trials and epidemiological studies to compare the effectiveness of different treatments or interventions. So from here, you can be able to see that the from this survival curve that is just an illustration, you can be able to see that by 100 years we shall not have any person who is a heavy smoker. So you can see this curve here that is showing that when we reach at about 90 something years, and you see where the zero line is at about maybe 95 or 94 around here. When we reach those number of years, we shall be having no survivor who is a heavy smoker. So likewise, you can be able to have a curve and be able to see that by a certain year or number of years, we may not have any survivors who are diabetic. In that regard, using what we call the survival curve information. And it takes a 5-year survival ratio. So survival data is also referred to as time to event data, and it requires a specific set of statistical methods for three main reasons. So you do not just arrive at survival data using cram work or using estimations, and therefore there are specific statistical methods that you have to use in order to calculate survival data. And we are saying it requires these specific statistical methods because of three main reasons. And one is that the duration times are always positive, that the time until an event of interest takes place cannot be less than 0. So in calculating in calculating survival data, you do not have figures that are negatives. They are always positive from 0 to infinity and so forth. And secondly, different measures are of interest depending on the research question, the context, among others. For instance, we could be interested in the probability that a cancer patient survives longer than 5 years. Or we could be interested in that the typical waiting time for a cab to arrive after having called a taxi company is this. Or we would want to look at how many out of 100 unemployed people are expected to have a job again after 2 months. So these are different measures, and the different measures are of interest depending on the research question. That is another reason we need to use statistical methods. The other reason is what we call censoring that we have looked at. That censoring is almost always an issue. So most of the time, the event occurred before the end of the study and the survival duration is known. However, sometimes the event is not yet observed at the end of the study. So suppose that we study the time until death of patients with breast cancer, luckily some patients will not die before the end of the study. So other times, another event takes place before the event of interest. For example, a cancer patient may die from a car accident. So these are the censoring questions that we are looking at. That before the event of study, you realize that another event that was not in your interest occurs, and therefore that means that that is a censorship event that has occurred. And like we said earlier on, they are ignored because then uh, your study must be free of bias. So if a cancer patient that you're studying that you expect that will die in an average year of 5 years dies from a from a car accident, then it means that it has no effect on your study, because then the patient has not died as a result of cancer, but as a result of another event. But also, even sometimes the patient withdraws from the study or moves to another country, so we cannot observe her survival time. So this means that the known person is lost to follow up, or it is a drop up or a dropout. So censoring can be seen in some sense as a type of missing data. And for these reasons, many standard descriptive statistics, hypothesis tests, and regression models are not appropriate for this kind of data. So specific statistical methods are required to take into account the fact that we miss the exact survival duration for some patients. So because the descriptive statistics such as mean, median, look at data that is absolute or that is there, relatively there. For example, hypothesis tests or regression models look at single years and look at data that is available. They may not tap into data that might miss, or they may not tap into missing data, and therefore it is not proper to use this specific this particular kind of statistical methods. So it is only important that we use the different statistical methods that we shall look at if we are to calculate survival data. So we know that they survived a certain amount of time until the end of the study, or until they withdrew, or until they died because of a different reason. But we do not know the exact survival time because they were able to withdraw before the study. So the common functions in survival analysis are in here. So we're not going to go too much into the details, but it is important to lay the foundation with the most common functions in survival analysis. So let T be the non-negative continuous random variable representing the time until the event of interest occurs. So we consider the following functions. One, we look at the survival function. Two, we look at the cumulative hazard function. And three, we look at the hazard function. These are the key functions that we use in survival analysis, not the aspects of hypothesis tests and so forth, because we've been able to look at the gaps that are involved in the use of those statistical measures. So we want to look at the survival function as an analysis for survival of individuals or a particular cohort. One, the most common one is the survival function for each t, meaning for each time, where we say S, the probability of S is that for each time t, the probability that the time until the event is greater than this time t, in other words, it models the probability that the event of interest happens after t. So here, if we wanted to look at each time, we are saying for the function t, which is represented in the probability of the time t, will equals to the probability that the event is the probability that the time until the event occurs is greater than this time. So if we looked at point at the age 30, the probability that an individual will die is greater than the particular time that is 30. Someone's hand is up. So in other words, it models the probability that the event of interest happens after t. So at the age 30, we module that the probability that someone or an individual or individuals in that groups in that study group will develop a complication of diabetes will be greater than the time 30. So in the context of our example mentioned above, it gives us the probability that a randomly selected patient will survive beyond the time 30 or the time t. So in other words, the curve takes more than t times to arrive, or an unemployed person will take more than t months to find a new job. And that is what we're looking at in when we're discussing survival function. So the survival function, which is ST, is a decreasing function, taking values of 0, 1, 0, 1, since it is a probability, and equal to 1 at t is equals to 0, and 0 at, at t is equals to infinity. And I'm thinking that since I did not include an example, probably for the next, okay, we have an example here for the survival function. So you can be able to see the survival function. So in the explanation of the survival function from this particular graph, uh, from this curve, you can be able to see the probability of survival running from 0 to 1 vertically, and the time or the period of an event occurring ranging from 0 to about 400. So that is time. We can look at it as in terms of months, or we can look at it in terms of years, we can look at it in terms of weeks. We can deliberate as an individual. You can deliberate on the time or the period that you would want to look at. However, what this means is that from this function definition, that the event for each time t, the probability that the time until the event occurs is greater than this time t would mean that if this was our time t, meaning 0, that the probability that an individual get would get diabetes would be beyond this time 0. It could be 1 or it could be 100 years. So in this regard, if we drew a line upwards, if we drew a line upwards up to about here, the probability that an individual from the age 0 would get a diabetes would be at the probability of about 0.5, and this would occur in 100 years. This is what this survival function would mean. And the explanation here is that the curve shows the proportion of individuals or experimental units who, as time goes on, have not experienced an event. As time progresses, events occur so that proportions who have not experienced the event decreases. So you can be able to see that the probability that someone may not be able to may be able to survive to the next years keeps reducing. from 100 to as it reduces in that regard. I don't know up to that extent if I am clear in that regard, because we've roughly spent about an hour, and my weather is also becoming a little harsh. We may not be able to listen to each other. So I'm requesting that if there are no questions to that regard, we can be able to end there. And if there are any questions or any comments, you can be able to make them straight away. Are there any questions or comments? Unfortunately, my voice is not very clear. But if we do not have any questions in that regard, I would request that we stop there and we continue from there tomorrow. So I don't know if there are any questions or any clarifications or any comments. You can actually have them. Yes,